Hello and welcome back to Calculus 3, section 16.4 on triple integrals. We are going to deal with triple integrals in rectangular coordinates. We're going to have rectangular integrals and general region integrals. So to start, first we are going to, again, go back through the iteration. So I have a single f of x, and then I have a representative delta x representative rectangle that stretches all the way up. And this is my delta x, and I get to write that the area under the curve is a to b f of x times dx. And then we went to figure out the volume on, we can do rectangular domain, it's okay. X, Y, Z with some surface. You have some surface on top, it's all whatever it is. And that surface up there is Z equals f of x comma y. And what we had was a representative French fry, which was dx dy. So when you are looking for volume, you had the double integral of f of xy, and then let's say dy dx from a to b, and dy from c to d. So you have went from the rectangle into a French fry, and now we are going to come up with a triple integral, and with this we can peek into the fourth dimension because you will have dx dy dz, and in addition to dx dy dz you will have function inside, right? So that's 4 dimensions. Accumulation of temperature, accumulation of energy inside the object, right? We have a lot of these concepts that we can discuss. But now, instead of having representative French fry, we can put whatever kind of domain, doesn't matter. We are actually not just looking at this object the way we did before. We are going to take a look at the, we're not looking at that, we're just looking at the inside of the box as W is equal to f of x, y, and z. Somewhere inside the object is going to be a representative ice cube, which will have dx, dy, and dz. So now, if you want to find the volume of the box, you will take the triple integral, not the volume of the box. Yeah, triple integral, volume of the box. Let's say dz, dy, dx from a to b, from c to d, from e to f as limits. And this would calculate the volume of the box. So say I have a box (6 by 3 by 2). just a standard box like the one we are sitting in right now. Now you could find volume 3 times 6 times 2, which is 36, and be done. But then you know the drill, right? The little kid you are tutoring says, why? Well, say no more. The volume is going to be the triple integral dz, dy, dx. Dx, well, x is going from 0 to 2. Usually, right, our x-axis goes this way. Y is going from 0 to 6. And z is going from 0 to 3. That's usually the way we put these things together. So now, how do you solve triple integral? Well, the same as a double integral. You do the inner integral first, and then you just work your way out. So this is further equal to, you have the 2 outer integrals from 2 and 6. And then you have z computed from 0 to 3, dy, dx. So that's going to be now double integral of 3 minus 0 is just 3, dy dx. When you integrate the inner integral again, that's 3y computed from 0 to 6. Still have dx to deal with. That's 18. So you have integral 0 to 2 of 18 dx, which is 18x, from 0 to 2, which is 36. So why simple if we can complicate things? So to find volume, we will set up the triple integral looking at the bounds from x and y and z and so on. And if we need a fourth dimension for whatever else, then we will have a function inside this integral. So if you want to talk about rectangular regions for the triple integral, you are again talking about integral that only has numbers in its limits. Now, the cases that we are interested in are the cases that actually have functions in limits, because those are the general shapes. Now, you do have egg problem for your project, and hopefully you boiled an egg and then you cut it half through, right, put on a paper, transferred on a square grid, and did some points fitting and so on to find equations. Hopefully you did one of those double integrals, because you can do that problem already because you had double integrals, right? You have a function on top that it's maybe a paraboloid or something, and you have a function on bottom which is half a circle, right? So now that's hyperbolic, that's elliptical paraboloid on top now, and hemisphere or half a ball on the bottom. Top minus bottom in the integral, right? You're figuring out the limits. You can actually, with the water displacement, when you check, you can get some pretty amazing results, depending on how well you can measure your water displacement. Usually students go to the chemistry lab and get one of those beakers that has the good, division on the side, precise, so they can figure this out. Now, that problem is perfect for double integrals. So what kind of problem are we going to work on with the triple integral, right? Well, as I said, you have two flavors. Flavor number one is volume, when you just have triple integral dv, and you have bulk, the fourth dimension, so this is a 3D, and you have a 4D version, which is triple integral f dv, right, f times dv. So for rectangular region, all limits are numbers, and you are just getting the box. for general region, we have some functions in limits of integration.
That would be the distinction between 3D and 4D, right?
No, that's just the way to set up the integral, whether you have the in limits. Remember that your integration was 0, 0, let's say 2, 2 and 6, and then 0, 2, and then negative square root, positive square root.
What you wrote just up there, the general region would be the bulk. Is that correct?
No, that this is completely. Both of these can be these, and this one can also be both of these.
Okay.
Because that depends on what they have in the limits, because the limits show what type of object you have. So let's work on some of the cool stuff and see what we can get here. Before we do that, I want to write the triple integral. And this will be the triple integral over region D from f of x, y, z dv is going to be the triple integral. So we have a to b, and then we have g of x and h of x, and then capital G of x, y, and capital H of x, y, and then we're going to have our f of x, y, z, and then we're going to have our dz, dy, dx. Now this is general region. General region. So what I'm going to do is, it's like a Band-Aid. Let's just take a problem and grind through it to figure out the way to put these limits. The most important skill for you guys is to be able to find the bounds for the object, to model it. Remember, calculating this, you stick it in the software in computes. The computer cannot still, right, yet, cannot set this integral up. When the computers can do that, then we are irrelevant, right? At this point, computers are going to compute this easily, but they can't really set this stuff up. So what I want to do is I want to take the Hodor over here, and I want to write the triple integral to compute the volume of this, and then we also can use the basic algebra, right, to compute the volume of this, because it's just a wedge, right? It's not a big deal. So let's work on this problem. So side view. Well, first of all, I'm just going to draw the object in a 3D realm over here. So the object is going to come down some x. It's going to go, it's long in the y direction. Maybe I should make it longer. There we go. So that's the y direction. And as you can see, you have your xy bottom. Guys, that's the bottom of the object, right? And then we go up to create the height of the object, and then we drop down. So it's just a wedge. now looking at this, right, object, I am going to, so what is the height of the object? The numbers. What's the height? 2, right? So the height is 2, the width is 1 inch, and the length of the entire is 6 inches. So we can actually compute the volume of this without using any calculus by simply saying that this is going to be 1/2 of the 1 times 2 times 6. So it's 6 inches cubed. That's the volume without using any calculus, because, right, if you have this wedge and then you put another one of this on top, they will create a box, right, a rectangle box. And you can, with the rectangle box, it's just because this is half of it, half of the rectangle box, and we say it's 6 inches cubed. So this particular object is 1 in width, that's your x dimension. It's 2 inches high, that's the z direction, and it's 6 inches long for the going across. Now I would like to set up a triple integral for this one and figure things out. Well, let's go and first take a look at the order. Do we want dx, dy, dz, dy, dz, dx, dz, dy, dx, or dx, dy, dz, or what do we want, right? You have 6 of those. Well, as you are looking at this object, you notice that you have few planes that are bounding this object. So I'll go with the one in the back, and that one, right, is the x equals 0 plane. In the back is x equals 0, and over here in front is x equals 1. So those two planes are front and the back. Guys, those are the triangles in front and the back of the object, okay? X equals 0 and x equals 1. Then I have the orange one here, which is the top piece, and that's y equals 0. Then I have the bottom of the object, and the bottom of the object is z equals 0. And finally, I have the Hodor, right, surface, which is a slanted plane, which we have to figure out. So I have the top over here, and that's going to be z equals plane. We have to figure it out. So now my object is bounded from all sides. See, I have z equals a function, and that is going to go into the limits, which means that z must be inside the integral. It cannot be at the end. There is no, you will have to rewind what I'm talking about in the video a few times to catch every single word of this. Z cannot be at the end of the integral, outer integral, because it has a function to it, because z equals a plane is going to be some function of x and y. Maybe just of x, maybe just of y, doesn't matter. But z is not a number on top. Z is a number on the bottom. Yeah, 0. But it's going to be 0 to some function. And that's what disqualifies z from being at the end of the integral. Now, looking at y's, on the left-hand side, I have this line also here that it's y equals to 6. So looking at the y's, y goes 0 to 6. And then looking at x's, x goes from 0 to 1. So both of those are number to number, and both of those are eligible to be at the end of the integral. So the best choice right now would be the z dy dx for this particular problem. But you can also use dz dx dy. That's also fine. We'll use the z dy dx. But you can also use the other one because y is 0 to 6. So that's another thing. Now, I have two jobs. First job is to figure out what is the equation of the plane, right? On top, the slanted one. And then my second job is to figure out the rest over here, which is the yeah, I lost my train of thought. Well, I have all the limits. I need to figure out the equation of the plane. Oh, and then I have to set up the base so we can set up the limit. So let's work on the plane. So plane. Top plane. How about that? Top plane. So how would I find the equation of this plane? Yes.
Can you look at it from the zy trace?
Excellent. We are going to go into a zy trace because in a zy trace it looks like that. So the plane is actually, so this is 2, this is 6, and the plane is infinite towards us in the, right, pouring out of the screen is infinite. This way, it's infinite into the board. And as you can see, this line defines it perfectly. X is not going to be present in this equation because this equation works for all x's that you can possibly imagine. So it suffices for me to find the equation of the linear line z, y. So I'm technically looking for just a linear line z equals, the slope over here is negative, as you can see, because it drops down. So slope is negative, 2 over 6, which is 1/3. So negative 1/3 x plus 2 would be my equation of the plane that goes up. That's what I said, y. Please pay attention. Thank you. So it's equation z in respect to y. Good. Now I am going to draw the domain. And my domain is always in xy plane. And if you carefully look at your domain, you have a 2, 6 rectangle. And remember, whatever one you consider, let's say you are considering dx, that's the one that goes on the end. Can you set it with dy? Yes, I said you can set it also as a dy, but then the y would go at the end. So I have everything ready to calculate the volume of this Hodor. We already agreed on a dz, dy, dx. Now if I look at my red picture, which is the domain, oh no, I have the picture wrong.
Yeah.
You all see that I have the picture wrong? It's the y value is that goes up to 6, not the x. So this picture is terrible. Need to fix this. Needs to look like this. There we go. Much better. So x value goes from 0 to 2. No, it's 0 to 1. X is 0 to 1 and y is to 6. Yes, holy nightmare. So that's when you swipe from 0, right, your dx. is going to swipe all the way to the right, and it's going to be 0 to 1. The y goes from 0 to 6. And the z goes from 0 to 2 minus 1/3 y. And now we compute this. So two integrals, 0, 0, 1, and 6. And now when I integrate z, it's going to be z from 0 to 2 minus 1/3 y. And I still have the y, and I still have the x. 0, 0, 1, 6. And now I am integrating 2 minus 1/3 y dy dx. Integral 0, 0. Oh no, I'm integrating now. So integrating respect to y, that's a 2y minus 1 over 6 y squared, computed from 0 to 6 dx. We better get 6 at the end. Is equal to 0 to 1. And now when I plug in 6, I get 12 minus 1 of the 6's cancels, and I get a 6 over there, dx. It's integral 0 to 1 of 6 dx. 6x from 0 to 1 is 6. Yeah, it's good when you go out with friends, you know. Comes up. You solve it quickly. So this would be one of the calculations. Yes?
Will we learn how to solve it when all three domains are functions, or that's not in the scope of this class?
It is, and yes, the answer is yes, but see, the trick is that your whatever is on the end is always going to use just numbers. So the object is going to have shapes from all sides, but your x will still go from 0 to 3.
So the key is when you're doing it to create it so at least one limit is numbers to set.
Yes. Of course, it's never too bad until it becomes bad. So we're just going to set up 15,000 of these to get comfortable. There is nothing else in this section. This is it, right? There are no other formulas. There is, right? Your ability to set this up is the only thing that technically counts. You know how to solve it. You do the inner integral, then the one in the middle, and then the one on the outside, right? Making sure that the outer integral is always having just numbers on the limit. So when you take a look at the homework page, which I just opened for you, you have all these wonderful, wonderful, wonderful shapes to set up. And obviously your homework will have even more in the, right? So we start with, if you take a look at the upper right, you have this triangular wedge. It's not a tetrahedron. Tetrahedron requires all the lengths to be the same. And then you have these, if you go to the next one to the right, like a little hump over there. Like most of these look like those, skateboard ramps and things. Well, youngsters can go and break their hips and noses and teeth. So all of these, right? All of these we can set them all up with trees. And as you can see on the side, they have a cone with a half a sphere, and then whatever the hell 23 is, right? This is another wedge, but this wedge has a circular back, as you can see on the bottom. So we can set all of these up. Again, the most important part over here is ability to set this up. Computation of this should not be an issue for any one of you at this point in life, right? You do the inner integral, then the middle, then the outer. So let's talk about problem. So we're going to set up now. This is, I think, problem 16. Yep, problem 16. And this problem has
It's all the same. Could we maybe do 23?
Oh yeah. Oh yeah.
Because yeah, that one's just thinking about it.
So we'll do this one, y equals x on this edge. On the bottom, obviously, is z equal to 0. The top is z equal to sine of y. And they give you this point, pi 0. And this point is 0, pi 0. And obviously you have the origin over here. Now what they did is they colored this part over here orange. And they colored the top blue to separate the area. But it's enough to one. Okay. So this is what we are looking at. Now, before I do anything, first of all, I immediately see z equals 0, z equals sine y, z is not, right? dz is not in the end, right? That's immediately. I know that because it has functions. But look what else I have. I have y equals 0 and y equal x. Well, that means also dy is not at the end. This is really important because now I eliminated both z and y from being at the end, which means that I am stuck with the z, dy, dx order. Guys, you have to figure out the order first from the picture. And then you get to set this stuff up. So I eliminated z because z equals y, that's a function. I eliminated y because I have y equal x as a function. So now I am stuck with the dz, dy, dx order. So now I am going to draw the domain y equal x, and as you can see, it is connecting into the y-axis. And it's connecting at pi. This is pi. This is 0. And this over here is my domain.
Professor,
Student.
couldn't you say it is dz, dy, dx, or dz, dx, dy, depending on whether you call the function y equals x or x equals y?
Yes.
Okay.
It brings in more headache, though.
Okay.
So now, since I have the x at the end, I draw my representative rectangle dx, and I am ready to set up the volume integral. Guys, there is no function in here, so it's just going to be a volume integral, dz, dy, dx. Z, 0 to sine y, y, 0 to x, and x 0 to pi. Oh, no, this is terrible. Okay, I have a mistake here. Who can tell me what my mistake is? I made a mistake. This is why it is so damn important to draw the domain every time. What is wrong with my setup? This is wrong. Wrong. Now, what's wrong? What's wrong?
And I'll sine of pi.
Sine of pi 0. Yeah, I can. One of the three integrals has wrong limits. Which one and why? One of the three integrals has wrong limits. Which one and why? Meditate on that one.
You can talk to others. Back in a second.
I feel like it's 0 to 7 dimensional.
Stop paying attention.
Yes. Yeah, you asked the question. At least you know what's going on then.
But once he answered that question, I just stopped. So
Then you were like, oh, and checked out.
Come on. He was like, oh yeah, all of you are above an 81. But he definitely doesn't matter. He's got a shit. What? Why is 0 to pi? Why is 0 to pi? Well, they can either one can be either. That's what I asked in the beginning. That's like the question I asked. Because he can call his limits with x, just saying it's 0 to y. Well, x is 0 to a function. But in this case, he's calling it y is 0. Do you see how like y equals x could be equal to 1? That's what I asked. I don't know what he's calling it. If you look at like, I think I got 4 points off just from stupid shit. Like, I didn't realize I needed to plug t in for one thing.
Oh, I got at least
It's
2
just a
points off
bunch of
for.
dumb
shit. Can we?
It's his y. Your y is wrong.
So how's your calc 1?
Pretty shitty.
What's wrong?
The bottom of y is a function to a point, not 0 to a point, right?
Wait, it's so much better.
Wait. It's what was right?
So,
Yeah.
minus points for someone?
No.
Oh.
No, it's plus points for me. Because I'm such a good student.
So guys, who can tell me what's wrong? Is it the blue, the red, or the black?
The red one.
No, red one is. Oh yeah, the red one. Yes, you're right. The red one is wrong. Why is the red one wrong?
I just replaced.
Is it? Look at the black representative rectangle. The ends of the black representative rectangle, the ends are y's. Is the bottom touching 0? Y equals 0? That's x-axis, right? It's not touching it. What's the bottom touching? It's touching the function x. And the top should be touching what? Pi. That's the correct limits. X on the bottom. So, drawing this representative rectangle and using it correctly is imperative. Look at this. This representative rectangle is the calculus 1 area between two curves deal, and then we are adding on top of that third dimension, which are z's. So my representative rectangle is going to swipe from 0 to pi, which are x's, and that is the blue stuff, 0 to pi. Now, the top of this representative rectangle is always writing y equal pi function, and that goes the red pi. And the bottom is always writing the y equal x function on the bottom. So this is the setup. And then you go and you compute, and you get your integral setup. So, by the way, this is what your exam 3 question or 2 questions look like. Setup, no one cares about calculating. Set up the integral, because you can always punch it in the computer and get number. Let's take a look at, we will. Let's do 19 first. Yeah, why not? Let's do 19. And then we'll do 23 by popular demand. Right? Right. Okay. So number 19, for those of you paying attention, we'll have the ramp so we are going to have a shape over here. This is a curve. So this is like a skateboard ramp. This point over here is 1. This point over here is 1. This point over here is ln 2. Now, the top surface is z equals e to the y. And that's the only thing they need to give us, because we really can't tell what kind of, curved surface that is. We need that information. The rest we can all find. They did give us more information, but it's completely redundant because they gave us points as well. So we can figure these things out. All right, so what else do I have? Well, if I have a top over there, I'll have some kind of bottom. And that's clearly z equals to 1. Because the whole ramp sits at the elevation z equals 1. There is nothing below, just air, right, below z equals 1. And then we have the sides. I have this side, and I have another side on the back. So what are my sides? Can anyone tell me the equations for sides?
X equals 0 and x equals 1.
Excellent. X equals 0 in the back, x equals 1. Those are planes. So there is a plane, this plane over here on the side. As you can see, that's the plane right there, and it's described by x equals 1. That's x equals 1. And the one in the back is the one that's touching that, so it's the one in the back. And that one is sitting on the y-axis, also x equals 1. X equals 0, sorry. X equals 0. And now I need the equation for the back over here. And what's in the back?
Y equals 0
y equals ln2. Good. So y equals ln2. Beautiful. So let's just, for the hell of it, list all of these that we have. So x is stuck in between 0 and 1. Y is stuck between 0 and ln2. And z is stuck between 0 and e to the y. Cool, huh? So we can again use our dz, dy, dx in this case. We will not be using this case for 23 for the next problem, but now we can. And the volume integral here is a triple integral. Do dz, dy, dx. X is 0 to 1. Y is 0 to ln2. And finally 0 to e to the y. And we are done. Green?
Would the limit be
Oh, 1, 2, yes, you're right. Thank you. 1 to e to the y for z. Yes. It will be 0 if the whole shape was all the way down to the... Yay! 23. I'm gonna draw this now. Let's see. Yeah. Thank you for picking this and no thank you at the same time, right? So we have our x and z axis, and then we have our y axis. Now we're going to have a shape that is going to be, okay, let me see if I can pull this one off real quick. So go. There we go. And then it's going to have, all right, so this part is all one part that folds to the other side, and then the orange is a different part. I know that. So here's what the shape looks like. It's on top of the page up there. Top of the page. And there is an equation for this one. Y equal 2x squared plus 3z squared. And I'm going to also call this one orange because it's y equals 9 minus x squared. Even though it's colored blue, both of these equations are y equal. So I know, because these two equations, I know that y cannot be at the end. Y has to be inside. So I want to think that we are going to use maybe dy, dz, dx, or something like that. Now this is all it's given to us. So what should I do? The first thing you do is, you know that most likely, right, this is not 100%, but most likely, you're going to have a triple integral that it's dy, let's say dz dx, let's say. And you know that the top function is 9 minus x squared and the bottom function is 2x squared plus 3z squared, because that much needs to be obvious, because the blue sits on top of the orange and it's top minus bottom. So the top function is 9 minus x squared, so goes in the upper limit. Now this is what we know 100%. I don't know anything else. How do I get the domain? Well, the domain is going to be you shine the light along y-axis and it's going to create some kind of a domain on the xz axis. Now, to find what that mathematically is, we set these two equations equal to each other, and that will give us the outline of the fattest part of the shape that will cast the shadow on the, and shadow is the domain. So to find the fattest part, look, you have a ball. You all know the ball, right? Basketball, baseball, I don't care. When you shine the light, you get a circle. How fat is the circle, the shadow? Well, as big as the ball where the equator, right? Where the fattest, right? The ball. So for all of the shapes that you are setting up, there are this weird kind of combination. You will shine the light along the axis that these equations are given to you, and that will reduce your equations down to something that you can deal with. You hope for a circle or something that you can deal with. So when I set these two equations equal to each other, I get 2x squared. Well, let me do this. Domain. 2x squared plus 3z squared is equal to 9 minus x squared. So that's where we start. Move x squared on the other side, you get 3x squared plus 3z squared equals to 9. And finally, yay, x squared plus z squared equals to 3. We just found that our domain is the circle with the radius root 3. This is my xz domain. And I have a root 3 radius. Now, when I draw my representative rectangle dx, because I'm going to put dx at the end, I am finally able to set up my volume integral. dy dz dx. Note that the dx is going to go from negative root 3 to positive root 3 on the picture. Are we green? What are my z values? So you are thinking of the top of the representative rectangle and the bottom of the representative rectangle. What functions do they ride? Yes, the middle one, yeah, z ones.
The 3 minus z equals square root of 3 minus x squared.
That's the top, and the bottom is a negative, right? So we have a negative root 3 minus x squared and positive 3 minus x squared for the limits. This should clearly say 3 minus x squared. And then finally our limits for 9 minus x squared on top and 2x squared plus 2z squared on the bottom. This would not be fun to compute because most likely you would have to use trig sub. Well, we're going to have cylindrical and spherical coordinates coming up for things that are rounded, and so we can deal with that. what you're staring here, guys, this is a perfect exam question. Set it up. That's it. Set up, move on. So do you all have the limits? We'll set one more up and then we'll go for a break when we come back. Cylindrical and spherical coordinates.
Fun stuff.
Yes. Is there anything that you guys would like to see from this next page of shapes that are given to you? Anything? Anyone?
That cylinder looking one at the top. Yeah, that was 2.5.
That one? All right.
Not pretty similar to the last one. Isn't it?
They all are. They all are.
Just breaking it down into trays.
Yes. So we are going to have a cylinder that it's cut problem 25. Cylinder x squared plus 4z squared equals to 4. And the two planes y equal 3 minus x and y equal x minus 3. So that's all that is given to us. And we just now need to figure out what to do. So we are going to shine the light on the y-axis. And if you take a look, the cylinder wraps around y. So we already know what the function, what the domain is, right? Because we're going to do this along the y-axis. So immediately the domain is going to be the xz plane. And you see that this is an ellipse, I hope. Because when you divide the 4, you get x squared over 4 plus z squared equals to 1. That's an ellipse. And the radius in x direction is 2. And in the y direction is 1. That's my domain. Now, The upper function is z equals square root of 1 minus x squared over 4. And the bottom function here is z equals negative square root of 1 minus x squared over 4. And we see that our x values are from negative 2 to 2. The y values are given to us by these functions. I just need to know which one is on top and which one is on the bottom. Right? 3 minus x or x minus 3. So we'll have to figure that out. So now, when I'm setting up the volume integral, I know the order. Z has functions to it. Y has functions to it. So we have to go with dy, dz, dx. X's are nicely lined up as negative 2 to 2. Z are the negative square root and a positive square root, which I already know what they are. 1 minus x squared over 4. 1 minus x squared over 4. Now I just have y equals x minus 3 and y equals 3 minus x. Which one goes on top? Which one goes on the bottom? Y 3 minus x and x minus 3, yeah. So which one would you put on top and why?
X minus 3 was 3 minus x equals negative x. But I just got a bunch. I don't really actually have to put it. No.
So which one goes on top and which one goes on the bottom?
Does it really matter?
Because you get negative volume. If you swap it, right? Because when you swap the limits of integration, the integral picks up a minus sign. So in that respect, actually, it doesn't matter, because when you compute, you get a negative, you just take a positive value for it, right? But it might mess up other things along the way, so we're not playing with the fire.
X minus 3 goes on the bottom. Because that's the negative portion of y. Or it's the further negative part of y.
So why break our heads when we can draw? Right? We can draw. I can just go and say, well, how about I just draw xy and see what's in store. The first one is negative 3 on the, so negative 3, and it goes, slope is 1. So it goes like that. So this is x minus 3. And the other one is 3 minus x. Goes like this. That's 3 minus x. So 3 minus x on top, and x minus 3 on the bottom, because you see that x is wedged in between of those two. Now where is your shape? Your shape is right here. This is your sideways shape. That's what the shape is. The red stuff is the shape. So you need to be able to cut these from sides and each way and just, argue which way the stuff would go. And if you ever get stuck, just keep drawing to visualize from a different angle, and then eventually it will, right? Now, the cool thing about this is the world around you is filled with objects. that you can measure and set these integrals for. Look at this console over here for projector. Right? Let's go. You measure it, and then you set up the integral. I want to know what the volume of this thing is. Right? Why do I need the volume? Well, how many of these I can fit in a box? Right? So these are all engineering feats that you have to figure out. You want to be a mechanical engineer? Well, hello. This is for mechanical engineers. Right? That's your life right there. Good. Take a break. When we come back, cylindrical and spherical integrals.